Hey AP Chemsters, this is hopefully the last edition of the notes from from chapter 12. We did not get to problem number 23. If you looked at 22 carefully, 22 sets up almost identically to problem number 23. So why don't you read it, study problem number 22, pause this and give yourself like 5-10 minutes, however long it takes, and then the answers will just magically appear when you turn on your recorder again. All right, ta-da! So the natural log of k to the first, or the first condition, plus the activation energy over r times 1 over t1 equals the natural log of the constant 2 plus the activation energy over r times 1 over t2. And there I just plugged in the numbers. That's my second line right here. So here I am just plugging in the numbers. Then what did I do? I kind of started simplifying. This is the natural log of 4.6 times 10 to the negative 2 is negative 3.08. How I got this number is I just multiplied these two together and took 1 over that, and that's where this number came from. I'll just clean up my math a little bit. And negative 2.51 is what natural log of 8.1 is, times 10 to the negative 2. There's a 10 to the negative 2 up here. And then EA times, and this is 1 over 8.3145 times 293. That's what this number is. So then I combine the EA terms, and I combine my integer numbers, or my numerical values. And so I added 3.08 to both sides and got 0.57. I subtracted EA 4 times 4.1 times 10 to the negative fourth. I took out the EA term. I did the subtraction. Here is equal to 0.57. Divided both sides by 3.1 times 10 to the negative fifth. And here's my answer. So it took about 18 kilojoules for this reaction to occur. All right, the beauty of doing the blank wall is that you can actually stop and re-listen to things again and again, and hopefully you're taking advantage of this. Here's our very last section, and it's a catalyst. A catalyst is a substance that will speed up the reaction itself, but it's not being consumed. We talked about that a couple chapters before, sections before, where it is the reactant in step 1 and it's the product in the last one anyway. So it's not being consumed, it's being regenerated. So it's being used up during the process, but it's being formed again. So that's why ozone and the chlorofluorocarbons are such a big deal, because it only takes a little bit of this free radical chlorine to create such havoc with the ozone. It doesn't get used up. It's always going to be there after we put the aerosol stuff in there. So what's the effect of it? The catalyst will lower the activation energy, but does not change. That should be a delta E, not a DE, for the reaction. It provides alternative reaction pathways, and it also results in a higher percentage of effective collisions. So let me kind of draw you this. So if we go back to that same activation energy, so this is energy and this is reaction progress. So this was the curve that we saw earlier. And so this is our reactants, these are our products, and up here was that mumbo jumbo of your activated complex. I'll just put an AC up here for activated complex. So what does a catalyst do? Well, that's what it says. It lowers the activation energy, but not the delta E for the reaction. Well, what's the change in energy? We have said this minus this. This is your delta H, or your energy change, right? So a catalyst is going to lower, I'll put that here, the catalyst will lower the activation energy, but doesn't change this right here. It doesn't change it. So a catalyst would do something like this. So here is with the catalyst, and here is without the catalyst. So it's a higher hill to climb. It requires more energy without a catalyst and with a catalyst. Now, there are such things as negative catalysts, and I was maybe telling you about that earlier when I was talking about medicine, where if I want a slow releasing medicine, you can have a negative catalyst and it'll make that hump even higher, which slows down the progress. All right, so it provides an alternate reaction pathway like your enzymes. Your enzymes are your catalysts and your biological processes, and they will affect the orientation so that the molecules can have an effective collision. So it's kind of like a jigsaw puzzle that the reactants will hop on board in the correct orientation, and then they're allowed to react in the correct process, or correct the orientation. I can't think of another word right now. So anyway, what else happens? A catalyst results in a higher percentage of effective collisions. That's because it lowers the activation energy, so you don't need as much energy, and it typically will change the process, the way the steric properties. We used that word last time. A heterogeneous catalyst, hetero means not the same, if you remember. It's usually a gaseous reactants on a solid surface. Typically, platinum is a good catalyst. I think copper is too, if I remember right. And so it just allows the surface. We saw this heterogeneous catalyst when we did the Diet Coke and Mentos outside. That the Diet Coke and the carbon dioxide was the gaseous reactants, the Mentos was the solid. It provided that surface for that thing to occur. So what's the four steps? The absorption and activation of the reactants refers to the collection of one substance on the surface of another substance. The migration of absorbed reactants on the surface, so they will go towards it. Then they will react, and then they will escape, or deabsorption or desorption. Uses is conversion of alkenes to alkanes as breaking that double bond. Conversion of carbon monoxide and nitrogen monoxide in auto exhaust to carbon dioxide and nitrogen gas. Homogeneous catalysts, they are in the same phase. And again, I've talked about this ozone thing. To me, that's like the prime example. So that freon, that's your aerosols, will go up into the air, and light, just, sunlight will decompose it into making these free radicals. The chlorine by itself catalyzes the decomposition of ozone like we talked about before. And notice, here is chlorine here. It's one of the reactants. It's used up in the step 1, but here it's a product. It is made again. It is, came right back. So one molecule of chlorine could then go on and attack another ozone molecule. And then it's going to be formed again. It can go on to attack another one. So notice that the chlorine gas, the atom, is not used up, which is the qualification to be a catalyst. This is also why small amounts of chlorofluorocarbons, such as freons, can do huge damage to the ozone layer. Hey guys, we're almost done. So here's problem number 24. Same as before. Why don't you take a few minutes out and do this on your own? Just don't write down what I do. You're not going to learn from that. So actually try this on your own and pause your whatever you're using and come back, and the answers will magically appear. All right, I hope this was a pretty straightforward problem for you. The reactants is X plus Y. The products are 2XY. Oops, I didn't write this down. What is X2, Y2? That's your activated complex. That's kind of when there's the process of breaking bonds and being attracted to the other one. It's called the activated complex. Label the chart above the activated energy and the overall change. So you can see where I did the activation energy in blue and the overall energy in red. So what's the value including units of the activation energy? It's just final minus initial, so it's just the 130 minus the 100. And then what's the overall change? I should go back here. It's not the final minus initial necessarily. It's the overall height of the hump. All right, so this is where you end up. This is your activation energy. Your overall energy, that's what's final minus initial. I apologize for that. That's 100 minus 50, so it's 50 kilojoules. Is this reaction endothermic? So hopefully you look at it and say it has to be endothermic. It's an overall increase of energy. Your delta H is a positive number. It has to be. So going on here, problem 29, same as before. Well, not quite. The graph looks a little different. So why don't you pause this, figure it out yourself, and then check your answers. All right, so how did you do? The reactants are AB plus C, products are A plus B, C. Hey, here's a bonus question. Well, not really. I'm not here to give you that. What kind of reaction is this? Think about it. Think about it. Hey, if you said single replacement, you're right. ABC, I wrote it down this time, is the activated complex. I labeled the charts. Blue is the activation energy. The red is the overall change. Activation energy is the top of the hump minus the amount of energy at the reactants. Actually, it took me a few minutes to actually figure out what that number was. I figured about 52. Hopefully, got something very similar. And then the overall change in energy is final minus initial, so it looks like about 18 minus 52. If your numbers are a tad off, okay, that's not a big deal. And negative 34 kilojoules. Is this X or endo? It is XOY because the delta H is negative, the overall lowering of energy. Okay, aren't these graphs cute? So anyway, it says according to the following graph, what's the impact of the catalyst on the reaction? Let's look at a couple things. Look at the number of particles that are colliding that don't have enough energy to react on the left hand right here. That is a huge amount of particles. So if I were to integrate, ooh, there's a calculus term for you. If I were to integrate the area underneath the curve, that'd be the total number of particles that don't have enough energy to react. That's a big amount. Right here is that these are the extra particles that do have enough energy to react as well. So this is the new activation energy with the catalyst, and the green is the originally only the ones that were able to have enough energy to react. So if I were to compare graphs here, this would relate to the top of the curve here. So what do you want to use? How about a crayon? That sounds like fun. So, oh, this is cute. So this would relate to here. Only a few particles have enough energy to go up and over this hump to go down to the products. Now with, let me pick a new crayon then, how about a red one? So if I take this amount, this is the additional number of particles that are able to go over that hump. So you have lowered the amount of energy, so more particles can react as well. And finally, I don't know what color do you want to use now. How about purple? This one is the overall that still can't go up and over the curve. So there's a lot of particles, so I guess it'd be up over here. Still hasn't made enough energy to go up and over the curve. So they're just sitting here on the reactant side. They aren't doing anything. They're just kind of sort of colliding with some energy, but not enough to break bonds and not enough to form the activated complex. So I guess I shouldn't put that here. I guess I should just keep the purple one about here on the reactant side. That probably makes a little bit more sense. All right, I think that is enough. Oh, you're supposed to do some more problems, it looks like. So anyway, I hope this helps. Again, write down your questions. Always feel free to text me. You know I answer those. Email me if you feel more comfortable doing that. Read your book, for heaven's sakes. It's there as a reference. You know, you're going to be going to college soon. That book, you have to start reading a book for college. You might as well start now. So I hope this helps. Take care. I really hope I see you tomorrow. Bye-bye.